Viewers, this is Walgembe Soap taking you through A-level physical chemistry. Now in this video, we are going to be covering the topic of physical equilibria. Now you are advised to pause on each and every slide to take the notes before I begin the explanations. You're advised to subscribe to the channel and also share this video to your friends so that you can benefit as a family. Now, physical equilibria. Physical equilibria is also called phase equilibria. Now, if you haven't taken the notes, pause the video before I begin the explanations. So, physical equilibria. Pause the video, take the notes, and resume the video. So we are saying that physical is the same as phase equilibria, and this is for physical chemistry. And we are saying that we are going to be involving the study of different states of substances. And here we are going to be looking at the solid, liquid, and gaseous states of different substances. Now we are going to be looking at different diagrams, and we are saying that solid, liquid, and gaseous states of a particular substance are also known as physical states because they are chemically indistinguishable. Now that's why the topic in general is called physical equilibria. Now we are saying that physical equilibrium is the equilibrium established between molecules of a substance in one physical state and molecules of another substance in the same physical state. Like we have given examples and we have told you from a solid to liquid, this can be an equilibrium, solid to liquid equilibrium. The reversible arrow is going to indicate equilibrium in the subsequent videos that you are going to be making. And you are saying that liquid to vapor equilibrium. I say that the reversible arrow is always going to represent equilibrium. That is to say, for example, liquid water getting converted to steam. And you are saying that also solid to vapor. Now in your O-level, you looked at all these processes. There is an equilibrium that exists between a solid turning to vapor. And you are going to be looking at that in details. Now the most important part where A-level begins from is here. You must be able to know the characteristics of a physical equilibrium. And you are saying that one of them is equilibrium is attained in a closed system. So you should note this because it's highly required. Equilibrium is attained in a closed system. At equilibrium, measurable properties of a system become constant. So this word constant, we are going to be using it often throughout this topic. So we are saying that at equilibrium, measurable properties of a system become constant, and that's something you should never forget. And we are saying that at equilibrium, there is a dynamic balance between two opposite processes, and that's why we use reversible arrows. This will show that between two different phases, a dynamic equilibrium exists, or a dynamic balance. So you are saying that each of the three homogeneous physical states of any substance can exist in term known as a phase. So the existence of these three states can be known as a phase. Now what's the definition of a phase? Now you should underline this and you bold it in your notes because it's very important to understand. We are saying that a phase is a homogeneous and physically distinct part of a system. Now note this, if we are to ask you the definition, we shall put here the marking points. Homogeneous and physically distinct. because for you to differentiate a phase, it must be physically seen and physically distinct. So we are saying that a phase is a homogeneous and physically distinct part of a system, which is separated by other parts by a definite boundary. So that means that the marking points in this definition is going to be the homogeneous and is going to be the physically distinct part of a system and also the definite boundary. So take note of that. A phase is a homogeneous and physically distinct part of a system which is separated from the other parts by a definite boundary. So a definition must contain homogeneous and physically distinct part of a system as one of the major keys, and then we must also see this word of definite boundary. Now we are saying that physical equilibria involves the study of conditions. And what are those conditions? Temperature, pressure, and concentration. But note that throughout this topic, we are going to keep temperature and pressure constant. And throughout the whole definitions that we shall give, we want to see these two items being kept constant. So physical equilibria, in all your definitions, we want conditions, and without those conditions, you will never be marked right. So we are saying that physical equilibria involves the study of the conditions, temperature, pressure, and concentration, under which different phases are in equilibrium. And we say that to show that phases are in equilibrium, on our phase diagram, we shall represent them with arrows, and these are going to be reversible arrows. So we are saying that equilibrium can only be achieved in a closed system. Now remember that we gave this one as one of our characteristics. When the rate of movement of molecules from one phase to another is exactly balanced by the opposing process. This is also explaining the use of reversible arrows, both in our phase diagrams and in our equations. So let's note down the following. We are saying that to differentiate a phase, now remember the definition of a phase. We say that a phase, now let's begin with the phase diagram of the one component system. And here we are going to look at three systems. We are going to look at the water system, we are going to look at the carbon dioxide system, and we are also going to look at the sulfur system. Now this is an example of a phase diagram, and it's going to explain what takes place when pressure is varied with temperature. So take note of that and pay attention and understand how it is explained. For those of you who don't have it, you pause the video and you draw it. So we are starting and we are saying that here the y-axis is showing that pressure is increasing and the x-axis is showing that temperature is increasing. Now here is how we plot the graph. You get a point of low temperature, let me say here, and then you extrapolate it. We draw a straight vertical line. You also get a point of low vapor pressure. You also draw a straight horizontal line. Now where they intersect will give the interpretation of the curve. So since these ones, low temperature and low pressure, they intersect in solid state, we shall be saying that at conditions of low temperature and low pressure, water is going to exist as solid state, or water is going to exist as ice. What about others? So if you look at if you had to consider conditions of high temperatures around 100, let's consider this. And then we draw this straight vertical line. And then this is high temperature. This means that temperature is high. And we keep pressure still low. So I'm going to extrapolate this very line. That means that at low pressure and high temperature, water is going to exist in vapor form, or is going to exist in gaseous state. So this is how we interpret phase diagrams of water. Now what about at high temperature and high pressure? So let me say that high temperatures around here, and I extrapolate this line. I draw a straight vertical line, and I also get a point of high pressure. I also extrapolate that line. Where they intersect will give me the interpretation of this curve. So they intersect in the liquid region. So that means that at conditions of high temperature and high vapor pressure, water is existing as a liquid. So let me hope interpretation of this graph has been clear to you. Now, what are these curves called? Now, these curves are named according to what is taking place. You should draw equilibrium arrows on these curves. Across these curves are indicating that liquid and vapor water are in equilibrium. That's why you put these reversible arrows here. So you should put those reversible arrows everywhere on the curve to show that both of those two states are in equilibrium. Now, these curves are named according to what is taking place. So if you are going this side, if you opt to go this side, this curve is going to be called the vaporization curve. Curve OB is going to be called the vaporization curve. Reason being, liquid is being converted to vapor. Or it can also be called the vapor pressure curve. And if you look at this curve, solid being converted to a liquid, this can be called curve, or it can be called the melting point curve. Or if you're going this side, liquid being converted to solid, the curve OA can be called the freezing point curve. So pay attention to that. And if you see a solid to liquid, this one curve OC, which is this one here. Since we are coming from a solid to liquid, or from a liquid to vapor, this one is called the sublimation curve. So let me hope you have understood. Now the point where the three curves intersect is called the triple point, and this case is O. So this triple point is where three phases coexist in equilibrium. So pay attention to that. And then we're having curve OD. Now curve OD simply means supercooling, and that's why it was presented in extrapolated format. So for those of you who have drawn the diagram, let me hope you have followed up. And now once you have not followed up and understood, rewind the video so that you can see things properly and you follow up closely. So let's proceed and see what's on the next slide. Now this next slide is explaining what I've already explained in the previous slide, and we are saying that at conditions of high temperature and low pressure, water exists as vapor. And now I extrapolated that and I showed you how you do that. At low pressure, you extrapolate that curve and you get a point which is at high temperature. Around here, you also extrapolate with a vertical line. Where they intersect, you should look at that state which is present and you find that it is the vapor state. So that's how we interpret phase diagram curves. And then at conditions of high temperature and conditions of high pressure, water is going to largely exist as liquid. And you do the same, you get a point of high pressure and high temperature. You extrapolate both of these points with straight lines. Where they intersect will give you the state which is present, and it's what is used to determine this, as we are saying, as the liquid. Now let's look at other lines. Now lines OB. Now these are the curves that I've told you we name, and I've already explained this in the previous slide. So for those of you who don't have the notes, you're advised to pause the video and first take the notes before we proceed. Now we are saying that line OB is the vapor pressure curve. Reason being is having an equilibrium from liquid to vapor. And what's that called? It's called vaporization. So we can either call it vapor pressure curve or the vaporization curve. So pay attention to that. Reason being, liquid water is being converted to vapor, and that's called vaporization. We name curves using the process that's taking place. So that curve will be called the vaporization curve. Now we are saying that it shows the effect of pressure on boiling point of water. Reason being, the y-axis of our curve is in terms of pressure, and remember, it's always the independent against the dependent. So we are saying that an increase in pressure results into increase in boiling point. I hope you have seen that. Now we are saying that at any particular temperature along this curve, the boiling point of liquid water gives the boiling point of liquid water. Reason being, along all that curve, everything is in equilibrium, and if you are to see that equilibrium I told you to draw, that means that there is a dynamic balance between the phase this side and the phase this side. So across that curve, both of those phases are in equilibrium. Now we are seeing that note. I want you to notice that always in physical equilibria definitions, you are going to have this word constant, and it's going to be constant temperature and pressure, like I said before as we are beginning the video. So I'm saying that boiling point is the constant temperature at which the liquid turns into a vapor. So boiling point is always the constant temperature at which our liquid is going to turn into the vapor. And we are saying line CO. What's line CO going to represent? Line CO is going to be our sublimation curve. Why is it the sublimation curve? I said that we name curves according to the process occurring. If you look at line CO, it's going to be between the solid and the vapor. And what's that process from solid to vapor? It's sublimation. So that's why we name that curve as the sublimation curve for our solid water or ice. So we are saying that it shows the combination of temperature and pressure at which ice and its vapor are in equilibrium, and that's the reason why we do this arrow across that curve. The reversible arrow will indicate that the two phases are in equilibrium. Now we are saying that the imaginary line OD, what does the imaginary line OD represent? We are saying that the imaginary line OD, it shows the condition known as supercooling. And let me hope you remember what we said about that. We said across supercooling occurs when temperatures over decrease with an increase in pressure, but we shall look at that later. So we are saying that supercooling is the process of lowering temperature of a liquid below its freezing point without becoming a solid, but that is not so important at a level. You just need to understand it. So you're saying that supercooling occurs when temperature is decreased with an increase in pressure. This is the ideal definition. Temperature is decreased with an increase in pressure. So pay attention to that. However, you just need to understand it. We are not going to examine it anywhere. Now proceeding, we are saying that line OA. What is line OA going to represent? Line OA. We are saying line OA is going to be the melting point curve. Now, why are we saying that the melting point curve? Look at that curve. It's between liquid and solid and liquid. And we saw it because of this equilibrium arrow. So if someone is going this side, you can call it the melting, the what? You can name it either according to the process of going this side going this side or this side. So that's why we are giving it two names. It can be in terms of melting, that is solid to liquid, or someone can name it in terms of freezing point curve. That's for the student who has considered liquid to solid. And I always advise this one, though both of them are right, because this one, we are going to be using this one mostly in our explanations. So I feel like you should be using this one the most, of liquid water. So what's that line showing? We are saying that that line is going to be showing that line is going to be showing the effect of pressure on the melting point of ice, or the freezing point of liquid water. And we're saying that the line shows the melting point of ice is lowered by an increase in pressure. Let me help you cover this experiment in your O-level physics, where we say that melting point of anything is lowered by increasing pressure. But this one is not very common at A level. Now where A level begins, the science begins from here, because this is a full question that we can award 6 marks. We ask you to explain why water expands on cooling but contracts on, why it expands on freezing but contracts on warming. So why is that the case? We are saying that when water freezes, its volume increases. Why? This is due to formation of stronger intermolecular hydrogen bonds. Now the strong intermolecular hydrogen bonds, now remember this is a water molecule. This is a separate water molecule. In water there are very many water molecules. Now between these water molecules we form what we call intermolecular hydrogen bonds. These imaginary lines, intermolecular hydrogen bonds, they form between a high electronegative element like oxygen and hydrogen. That's why we call them intermolecular hydrogen bonds. Now between these water molecules, they form intermolecular hydrogen bonds within each other. Now as a result, these intermolecular hydrogen bonds become spaced, and they lead to formation of a structure which is called the open tetrahedral structure. Let me help you see it as I sketched it. Now this structure is full of spaces. If you can look at this space, you 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 look at this space. When they are forming, they form on when water is cooling, and they form these structures which leave very large spaces in them. So you find that the more water cools or freezes, the more spaces are formed within this water. And you find that the more spaces are formed, the more the volume increases. And that's why we are saying that when water freezes, its volume increases due to formation of stronger intermolecular hydrogen bonds. And these hydrogen bonds, it's formation of an tetrahedral open-like structure with a lot of spaces in between this ice molecule, which eventually leads to an increase in volume. So that's the reason why water expands on freezing. Now what happens when you apply pressure to this structure that we created? Now when you apply pressure to this structure we created, these intermolecular hydrogen bonds are going to be destroyed. They are going to be broken, and once they are broken, that means that these air spaces are going to collapse also. So that means that water is going to melt. That's why we say that increase in pressure lowers the melting point of ice. So what we're saying here, when pressure is applied to this structure, the hydrogen bonds break down. And what happens when they break down? All of these hydrogen bonds are going to be broken. And once they are broken, these air spaces are going to be lost. And once the air spaces are going to be lost, the volume decreases. On cooling or freezing, volume is going to increase, but when you apply pressure onto that frozen ice or solid ice, it's going to melt, because hydrogen bonds holding that structure are being broken down and the air spaces are being collapsed. So that means that water is going to melt. So we are saying that when pressure is applied to this structure, the hydrogen bonds are going to break down, and as a result the opening structure is going to be destroyed, making ice to melt. So let me hope that has been simple to understand. Now in this slide, we are telling you to note down the following, and we are saying that melting points of bismuth and antimony also decrease with an increase in pressure. So you should note that bismuth and antimony, so you should underline this in your notes. For those of you who don't have the notes, always first pause the video and you take the notes and then you proceed with the explanations. So we are saying that bismuth and antimony, they all perform like water. Their melting points are going to decrease with an increase in pressure, and I've explained that. So proceeding, we have the point O, and I've told you point O is always a triple point, like I already explained. Refer back to your diagram, and you're saying that a triple point is a point that shows conditions of temperature and pressure. We may ask you for the definition of triple point. Like I said earlier on, physical equilibria, in all your definitions, we expect conditions of temperature and pressure. At least you need to have this word. It may carry a half a mark for your definitions, under which all three phases coexist in equilibrium. So triple point, as the name suggests, is a point point that shows that conditions of temperature and pressure in which three phases coexist in equilibrium with each other. Then what about the critical point? Now I didn't talk about the critical point. The critical point is always the last point on your phase diagram. So the critical point is located here. I think, I don't know, I didn't explain it. So the critical point is located here, and it is the point beyond which a gas cannot be liquefied, however much pressure is applied. That means that even if you increase the pressure like how, this gas here cannot be liquefied to water. So we define a critical point as a point above which liquefaction of a vapor is impossible, however much pressure is increased. So pay attention to this and don't forget it. A critical point is simply a point above which liquefaction of a vapor is impossible, however much pressure is increased. So that was the explanation for water system. Now we are going to explain the one for carbon dioxide system. Now for carbon dioxide, naming of curves is going to remain the same, but the curve structure looks different. If you look at OA, OA is slanting going this side, but for water, it was slanting going this side. And we gave an explanation for that. Reason being, water when it's cooling, it expands, and we gave the reason why it expands. And we also gave the reason why increasing pressure will increase its melting point. And then we also we say that these curves, all of them must have reversible arrows. When I was drawing them, I didn't include them, so you are supposed to fit them in your notes. For those of you who don't have the notes, you are advised to pause the video and then you first take the notes. So let's proceed. Now you're seeing that carbon dioxide is an example of a substance whose melting point increases with increasing pressure. Now let's look at it. So the graphs are always vapor pressure measured in atmospheres against temperature, which is measured in degrees Celsius. So we are saying that the above phase diagram differs from that of water in the following ways. We have already looked at this curve OA, and we are saying that line OA slopes away from the vapor pressure axis, indicating that the melting point of solid carbon dioxide increases with an increase in pressure. And that was not the case with water. For reason being, for water when it's cooling, it expands, but for gas when it's cooling, it contracts. That's the difference. And you're saying that this is because molecules of carbon dioxide in solid phase are packed more than that in liquid phase, unlike water. Because gases, their molecules are spaced, and on cooling, there is no force. There are no intermolecular hydrogen bonds like those ones in water to hold them. So these gases are just going to be brought together so that they just pack together in one place. So you find that on cooling, they are going to be compact, and that means that gases on cooling, they contract, which is not the case with water. Water forms intermolecular hydrogen bonds, and those intermolecular hydrogen bonds, they combine and form a tetrahedral pen-like structure with a lot of spaces within the water as a whole or as a compound. That means that on contracting, they are going to have an increase in volume. That's when you freeze liquid water. But when you freeze liquid carbon dioxide, it is going to contract because it lacks any bonds to form within its molecules. Otherwise, its molecules are just going to be packed closely together on freezing, so it's going to contract instead. So you're saying that the triple point of carbon dioxide occurs at a higher vapor pressure than that of water. Now these are some of the exceptions that can be concluded from the graph of water and that of carbon dioxide. Now we are saying that at a system, if you look at that graph and you're saying that a system at point X, we are saying that the system at point X is in solid phase and changes to vapor phase along XY when heated at reduced pressure. And sublimation takes place along XY. Now if you look at that graph, if you have to draw that graph is like this. Remember that this is pressure and this is temperature. So point X is around here and this graph extends going down. If you look at that graph, it comes from point X to point Y. Now what's happening? If you look at the pressure curve, pressure is decreasing. But if you look at temperature curve, temperature is increasing. Pressure is decreasing, temperature is increasing. So that means that from here, from this point to this point, we are decreasing pressure as we are moving along X to Y. We are decreasing pressure, but we are increasing temperature. So that's why we are saying that for sublimation to take place, we must eat this solid here, but we must heat it with a decreasing pressure. We are increasing temperature, but with a decrease in pressure, so that we can favor sublimation along point X to point Y. Now, if you look at from point Y, this line here must be vertical. I think I didn't draw it vertical. You must make it vertical in your sketch. Reason being, we are saying that at point Y, the system is in vapor phase, and then when compression means increasing pressure but leaving temperature constant. That's why I'm telling you that temperature must be constant. So this graph here from Y to Z, this one must be vertical upwards. That means that you're only increasing pressure. You're only increasing pressure and you're leaving temperature constant. So you're saying that when compressed at a constant temperature, it changes to a liquid, and that's along Y to Z. Let me hope that has been simple to understand. Now point O is the triple point of carbon dioxide, and we are saying that it's greater than 1 at 1 atmosphere. This implies that solid carbon dioxide boils without passing through the liquid state, but that's not so important. So let's proceed to the one component system of the sulfur. We studied 3 phases. We studied that one for water, and we studied that one for carbon dioxide. We studied that one for sulfur, carbon dioxide, and water. There are only 3 phases. So let's proceed. Now we are saying that sulfur allotrophically exists in two different forms. We have rhombic sulfur and then monoclinic sulfur. But at room temperature, sulfur usually exists as rhombic. Now, when we vary temperature and pressure, we are going to see that if rhombic sulfur will transit to monoclinic. The change from rhombic sulfur to monoclinic is called transition, and we are going to be looking at that in the next slide. Now we are saying that at ordinary temperatures, the stable allotrope is the rhombic form. I've already talked about that. Now you're saying that if the temperature at which the two allotropes are in equilibrium is called transition temperature, which is always 96 degrees Celsius. So you're saying that the temperature at which two allotropes are in equilibrium, that is the rhombic sulfur and monoclinic sulfur, is called the transition temperature. And the curve, since it's called the transition temperature, that means that the curve that will separate their equilibrium is going to be called the transition curve. So the temperature is not that important, even if you don't from it. You can leave out the temperature. Now going to its phase diagram. Now first of all, we are saying that when rhombic sulfur is gently heated, it is converted to monoclinic sulfur. That's why I told you at room temperature, rhombic sulfur is the one which is stable, but on heating it slightly and gently, it gets converted or it transits. That's the correct chemistry word to use. It transits to monoclinic sulfur. And you are saying that further heating results into monoclinic sulfur changing to liquid sulfur. So let's try to explain this graph. I told you for these graphs here, you are going to put equilibrium signs. I didn't include them as I was sketching them. So you make sure that you put all those reversible signs everywhere and don't miss them out. So let's look at the graph. I told you when you're naming curves, you look at what is taking place. So you look at the process that is taking place. And also for sulfur, you'll be looking at what sulfur you are dealing with. Like if you look at this phase and this phase, this is showing that rhombic sulfur, solid rhombic sulfur is getting converted to vapor sulfur. And what is the process of converting a solid to vapor? It's called sublimation. So this is going curve AB is going to be called the sublimation curve of what? Of rhombic sulfur. And if you look at curve EF is from solid rhombic sulfur to what? To liquid sulfur. So curve, since it's from a solid to liquid, or it can be from a liquid to solid, it can either be the melting point curve of rhombic sulfur, or another student can say it's the freezing point curve of rhombic sulfur. So that's with curve EF from here up to here. So you look at another curve. If you look at curve BE is rhombic sulfur getting converted to monoclinic sulfur. Now I already told you that in the previous slide, and I told you we call that transition temperature or transition state. And the curve that separates the two allotropic forms is always called the transition curve because it is showing that rhombic sulfur is transiting to monoclinic sulfur. Now if you look at curve BC, it's combining monoclinic sulfur and vapor sulfur, and it's a solid to vapor. That process is called sublimation. So that means that curve BC is going to be called the sublimation curve. We name curves according to the process taking place at that curve. So solid monoclinic sulfur getting converted to vapor sulfur is going to give us a sublimation curve, and that sublimation curve is going to be for monoclinic sulfur. Now which other curve is left? We can look at this curve. This curve is from solid monoclinic sulfur to liquid, and what's that process? It's melting. So curve CE is going to be called the melting point curve of solid monoclinic sulfur, and that solid monoclinic sulfur is going to be converted to liquid monoclinic sulfur. So pay attention to that. And then we have curve CD, this curve here. Now this curve here is from liquid sulfur to vapor sulfur, or from vapor to liquid, but you usually name it this way, liquid to vapor, and that's called vaporization. So this is the vaporization curve of sulfur generally, because it involves a liquid turning to a vapor, and we say naming of a curve, we name a curve according to the process taking place. So point D, since it's at the extreme end, point D is going to be our critical point. And we say the critical point is a point beyond which a vapor cannot be liquefied, however much pressure is increased. So pay attention to that. Now let's start going through what I wrote down. Now you're saying that curve AB is a sublimation curve of rhombic sulfur, and I've already explained that. And you're saying that curve BC is a sublimation curve of monoclinic sulfur. Curve CD is a vaporization curve of liquid sulfur. I think we have already looked at that. And in this slide, you are going to be looking at what I've already explained. So it's better to pause the slide and you take the notes, because all what is present, we have explained it. So curve BE, as we explained, is going to be the transition curve. Reason for the transition curve is because the transition we are having it separate into allotropic forms of sulfur, and that's the rhombic sulfur and the monoclinic sulfur. So it's called the transition curve. Now curve CE. Curve CE is a fusion curve for monoclinic sulfur. Fusion curve can also be called the freezing point curve. So you can change this one if you want. Fusion curve can be called the freezing point curve. We say that you name curves according to the process that is taking place. What about point B? Point B is a triple point of rhombic sulfur. Now I didn't name these points, but I've already explained what a triple point means. But for this case, after naming a triple point, you have to name the phases that exist at that triple point, because you have more than one allotropic form of a substance. That's why for every triple point I was naming, I was saying that curve point B is going to be the triple point, but for the triple point for which phases? Point B was a triple point for rhombic sulfur, monoclinic sulfur, and vapor sulfur. And if you look at point C is the triple point also, but it's for which points? So it's going to be for monoclinic sulfur, liquid sulfur, and the vapor sulfur. So we have three critical points. If you go back and you look at your curve, there are those points. It's a junction of three phases, and you have to state all those phases. You have to state the phase here, you have to state the phase here, and you have to state the phase here. So you're saying that point E is the triple point for rhombic sulfur, monoclinic sulfur, and liquid sulfur. And you're saying that point D is the critical point. I've told you it's always the point beyond which a gas cannot be liquefied, however much pressure is increased. So don't forget that. It's a simple definition. Point beyond which a gas can never be liquefied, however much pressure is exerted. So proceeding, we are saying that when any of the phases is subjected to a change in temperature or pressure, when any change is subjected to a change in temperature or pressure, it will disappear and another dominates. That's why we looked at rhombic sulfur transiting to monoclinic. But now there's that dotted line that I've already explained with carbon dioxide, and I gave it the same points. Also here, we are saying that X when heated at reduced pressure along xy, it undergoes sublimation. And what undergoes sublimation? First of all, it undergoes sublimation. Rhombic turns to monoclinic sulfur, and from monoclinic sulfur it turns to vapor. If you look at that curve properly, you interpret and you see that occurring. We are saying that sulfur at point Y is in vapor state. When it is compressed, I told you compression refers at keeping temperature constant and increasing pressure. So when increased pressure, when temperature is kept constant, we are going to have a change from vapor to liquid along YZ. So let me hope that's very simple to understand. Now we have left the one component system and we have went to the two component system. Now in this two component system is where we are going to look at mainly the eutectic mixture. So this video is going to be covering mainly the eutectic mixture. The liquid to liquid equilibrium mixtures are going to be covered in the next video. So make sure that you take your notes properly and you wait for the next video to be uploaded. It's going to be about liquid to liquid equilibrium. And to easily access those videos, simply go to the channel, click in that icon you're seeing, and you go to playlists. In playlists you find 3 playlists. There's inorganic chemistry, organic chemistry, and physical. So you opt for the physical chemistry playlist and then you hunt for the video of physical equilibria, which will be the part 2. Now let's handle what's going to be covered in this video, and it's going to be covered fully. We are going to look at solid to liquid equilibrium mixtures for eutectic mixtures. For those of you who don't have the notes, you're advised to pause the video and then you take the notes properly. So we are saying that when a liquid form of a pure substance, is cooled, it undergoes some changes. But remember, we must be cooling at a constant temperature. We are saying that a certain temperature is reached when a liquid is converted to its solid state at a constant temperature and pressure. Like I've already told you earlier, physical equilibrium, we are going to be making temperature and pressure constant because these are the major things that we focus onto. So we are saying that the constant temperature at which a solid and liquid forms a pure substance are in equilibrium with each other and is called the freezing point. So how can you define the freezing point? Whenever you are defining a point, whether boiling point or freezing point or melting point, your definition must always contain constant temperature because it's a constant temperature at which those points are obtained. So you are saying that freezing point is a constant temperature at which a solid and liquid forms of a pure substance are going to coexist in equilibrium. So make sure that you remember that definition. The marking points are going to be the constant temperature. And then also we want to see the pure substance. And then we want to see the word equilibrium. So make sure you take note of that as you are defining these definitions. So we are saying that below the freezing points, the liquid will change completely into the solid. So the freezing point is that temperature at which the solid and liquid form of a pure substance are in equilibrium. So if we continue freezing below that point, that means that the liquid is going to completely turn into a solid, and that's what this statement is meaning. So let's go to the next slide and look at what we are trying to explain. Now this refers to the cooling curve. This is called the cooling curve, and such a cooling curve is always for a substance in its pure form. Now I want you to notice that for substances in pure form is where we're having this kind of trough. If you're having a mixture, this kind of trough cannot happen. So how are we going to explain this graph? Now this graph is temperature is temperature, and this temperature is against time. Temperature is measured in degrees Celsius and time is measured in minutes. So we are going to divide this curve into parts. We are going to see from A to B, and then you are going to have from B to C. Now B to C, remember that this is a trough, and then you are going to have this constant temperature. That's why it's very important to define your definition of points as constant temperature. So always this constant temperature is always what is going to give us the freezing point or melting point of anything. And then there's what we call further decrease. So here at these constant temperatures where we have an equilibrium between two different states like a solid and a liquid. So let's look at the individual explanations. So we are saying that along AB what is taking place? Molten lead is cooling as temperature decreases steadily. Are you seeing what is happening? This is temperature. When you are going up, it increases, but this graph is going down. So that means that we are having a decrease in temperature. So along AB, remember this is molten lead. It has been heated to melt. So we are cooling it. So temperature is going to be falling. Temperature of molten lead is going to be falling, and it's going to be falling up to point B. That's why we are saying that molten lead is cooling steadily along AB. And then if you look at CD, along CD, an equilibrium is established between liquid lead or molten lead and then solid lead, and that's where is the freezing point. And remember that it's at a constant temperature. That's why when we're defining a melting point or freezing point, we always want that word because it's major. Let me hope you have seen it at the graph. The graph shows that it's a constant temperature, and it must be inclusive even when we ask you or we examine you to draw that sketch. So how are you going to explain that? So along CD, that means that T, let me hope we are seeing, we extrapolated the temperature. We are saying that this temperature is constant. This is going to be our freezing point of molten lead because it's a constant temperature at which both solid lead is going to be existing in equilibrium with molten lead. Below that, all the molten lead is going to solidify, and that's for this downfall. Now what are we saying? BC, curve BC. Remember I've told you for BC, we only get this trough here. We only get this trough here down with pure molten components. We cannot get this trough here from mixtures or from any mixed compound. So we are saying that line BC, and we are saying that line BC shows a condition known as supercooling, which you already defined. That's why I'm telling you that supercooling is only going to happen to pure components of a substance. With a mixture, don't put this curve anywhere because it doesn't exist. So we are saying that is supercooling, and we are saying that however after the first crystal is formed, it is absorbed from the surrounding, and after further solidification occurs at a constant temperature. So that means that T is the freezing point because T is a temperature at which both molten lead and solid lead coexisted in equilibrium. That's why we are calling it either the freezing point or melting point of lead. So that's it for the slide. Now for this slide, we are telling you to note, and what we are noting are these. We are saying that the freezing point of liquid is depressed when another substance is added to it. Let me hope you looked at that in physical properties of direct substances, which is colligative properties. In colligative properties, we told you that the more the number of non-volatile solid particles are present in solution, the more the freezing point is depressed. And this is the concept that we are telling you here. So we are telling you that freezing point of a liquid is depressed the more when another substance is added to it. So it's the same concept. And we are seeing that the decrease in freezing point, is approximately proportional to the relative amount of a substance or solid being added. So pay attention to that. And this is what I've explained earlier. I've told you that how much you are going to decrease the freezing point is going to depend on the number of non-volatile solid particles we have added to that liquid mixture. So we are saying that when plotting cooling curves for mixtures, they are going to be obtained by varying amounts of each component in the mixture. However, we are going to be using equal total mass. Now, assuming that we have to carry out an experiment, we get molten lead, and we say that we are going to use 50 grams specifically for this experiment. We make sure that we use equal total mass in each and every experiment. Each and every barrel must have 50 grams so that we can get comparable results. So, what we are going to do, we want mixtures. Now, these mixtures are only going to vary in composition, but all of them are going to remain with equal total mass. So this mixture, we can say that we want 25% tin. Let's say we are going to combine tin and lead, and then we are going to say 25% tin, and then the other percentage is going to be 75% lead. What we vary in this mixture is going to be the composition, and then this one we may say that we want 40% tin, and then 60% lead. We use the same components, but we vary the compositions. Then this one is a 30% tin, and then 70% lead. Now remember that these things are in solid form. So when you are preparing these experiments, we always first get pure substances, and that's why I first gave you a curve for a pure substance. You get a pure substance and then you melt it after heating it, because lead at room temperature is a solid. So we melt them and we get their liquids, and then we start cooling them. Pure substance, we have looked at the graph of a pure substance, and I've told you it's only pure substances that are going to give us this cooling trough, which is here. So for mixtures, we shall not get that supercooling curve, which is that trough going down. So we are saying that for cooling curves for mixtures, they are obtained by varying the amount of each component in the mixture, which I've explained here. And we are saying that, and then determining the temperature at which each mixture begins to freeze. Now notice that after measuring these components, after measuring these mixtures, the 25% tin and 75% lead, or 40% tin and 60% lead, or 30% tin and 70% lead, after measuring them, we melt them because they're in solids. When we combine them, we heat them to melt so that we can get liquids, so that you can get liquid mixtures, because in this topic we strictly use liquid mixtures. And then we are saying by varying amount of each component in the mixture, and then determining the temperature at which each mixture begins to freeze at each composition. So we are saying that the component with a higher composition, now pay attention to this, the component with a higher composition is going to solidify out first. Now if you have this curve, if you're having this bowl, and this bowl you're having 25% tin and 75% lead, that means that if you are to start cooling this mixture in this bowl, it's going to, in this bowl, this means that the one with the highest composition, so lead is having 75%, is going to crystallize out first when you are cooling this mixture. And then this one with the lowest composition is not going to crystallize out, implying that this one with the lowest composition is going to remain in the mixture, but this one is going to solidify out first because it's having the highest composition. If you look at this one is having 40% lead and 60%, 40% tin and 60% lead. So that means that the one with the 60% lead, 60% lead is going to be crystallizing out first because its composition is higher, and the one with the 40%, which is tin, is going to remain the liquid mixture. So pay attention to that. And the same applies to this. The 30% is going to remain, and the 70% is going to start crystallizing out. The one with the highest composition on cooling is the one that starts to crystallize out first. So that's the meaning of this statement. So let's proceed. So in this statement, we are looking at consider. If you have to look at this second statement here, we are saying that consider the cooling curve of liquid tin and lead mixture. And we are saying that the given composition are liquid tin is going to be 25%, and then liquid lead is going to be 75%. That means that when you are cooling these ones here, lead is going to crystallize out first, or solidify out first, or separate out first. The what is common, or what you find to be easier to you. And then you are saying that the percentages are always by mass. Is cooled at a fixed pressure and temperature. We are saying that a temperature T1 is reached when solid lead begins to crystallize out. And we are saying that lead is the one which is going to be crystallizing out because it has the highest composition. It has the higher composition in the mixture. Therefore, it's going to separate out of the mixture first. Now you're saying that this temperature will be lower than the actual freezing point of molten lead. Now if you pay attention to this, lead is having the highest composition and tin is having the lowest composition. That means that tin is the solid that is being added to lead. That's why tin is having low composition. And the more we add a solid to another, that means that we are going to be depressing or decreasing its freezing point. Let me hope you looked at that in colligative properties. And that same topic is going to be uploaded here on this channel. So we are saying that as cooling is continued, crystallization of lead makes the liquid mixture less richer in lead. Now what do we mean? Remember when we molten this mixture containing 25% tin and 75% lead, and we started cooling, now this liquid lead started separating out. It started crystallizing out of that mixture, implying that lead is leaving that mixture. The more we cool, the more lead leaves that mixture. In terms of crystals, it starts getting out. But the other one, which is tin, it remains with its composition the same because it's not crystallizing out. It's only the one with the highest composition that is crystallizing out. So we are saying that time is going to come when tin, which is not crystallizing out of the liquid mixture, is going to be the one which is more richer in the mixture. And this one, which is crystallizing out, is going to become less present in that mixture. And that's the meaning of this third statement. We are saying that as cooling is continued, crystallization of lead makes the liquid mixture less richer in lead until a certain composition is reached where both components solidify out together. Now notice that this temperature where both elements solidify out together is important in this topic, and it's called the Eutectic temperature. The temperature at which both components in the mixture crystallize out together, and you are going to look at that in the next slide. Let's look at the explanation of this curve. Now this is the cooling curve for a mixture. You can add an heading to it to prevent forgetting. Now what's so unique about this cooling curve of a mixture? You look at it, the cooling curve of a mixture does not have the other supercooling curve, and it's what I was emphasizing. With a mixture, that supercooling curve does not exist. It's only this. To be plotted, the graph will be looking like this, and we can ask you properly on how to plot it and how to explain it. So you are saying, plot this graph and then explain it. The graph is always temperature against time for the cooling curves. Now remember, a mixture, I told you we first molten it, so it's going to be a liquid mixture. So it's going to start by cooling. From curve A to B, it's so steep and it's going to be cooling because the liquid mixture is going to be cooling since it is from molten state. But when it reaches point B, now I told you it depends on the composition. Here we are using 25% tin, 25% tin, and you're also using 75% lead. And you say that the component with the highest composition solidifies out first. So when we reach that point B is where the point with the highest composition starts solidifying out. So along AB, liquid mixtures cooling, but at point B, from point B to C, solid lead is going to be crystallizing out. And we say that the more lead crystallizes out of the mixture, it is going to make the liquid mixture more richer than the other component which is not crystallizing out. And in this case, it's going to be tin. So let me hope you have got that. Now, lead continues to crystallize out until point C is reached. Now at point C is a point where a constant temperature is attained. And at this constant temperature, both of the components in the mixture, the liquid mixture, both lead and tin, are going to crystallize out. So let me hope you note that temperature. And always this temperature, if it open to our phase diagrams, is going to be called the eutectic temperature. Now, so beyond this, from D to E, there's going to be cooling of our solid mixture. So let me hope that has been simple to understand. So let's first go through the notes. So you're saying that along AB, the liquid mixture is cooling, just like I stated. And we're saying that along BC, lead is crystallizing out of the mixture. Why is the lead the one crystallizing out of the mixture? The reason for that is because lead is having the highest composition in the mixture. So pay attention to that. And then along CD, what's happening along CD? Along CD, both lead and tin are solidifying or crystallizing out. And what's the impact of that? That means that the whole liquid mixture is now a solid. There is no liquid anywhere in our mixture. Now along DE, our solid mixture is going to be cooling because there's nothing to cool further than a solid. Now notice that we are saying that points T1 and T2 are known as the arrest points. Arrest points can also be called freezing points. And these are arrest points or freezing points of lead. And the mixture here is where, remember that T1 is where lead starts to crystallize out. And the reason for that is because lead is having the highest composition in the mixture. And point T2 is where both of the components in the mixture crystallize out. And we have said that that's called the eutectic temperature, where two components of the liquid mixture are solidifying out. But we shall look at that more in details in the next slide. So let's jump on to the next slide. So here you're having a simple question. Now in this simple question, we're asking you, explain how phase diagrams of solid to liquid mixture. A solid to liquid mixture can also be called an eutectic mixture. So we are saying that explain how a phase diagram. Now we are going to look at these diagrams. How a phase diagram of a solid to liquid mixture or eutectic mixture can be obtained. Now remember that these phase diagrams, I told you, we need to get arrest points or freezing points of, first of all, pure components. And after getting the pure components, you mix various mixtures together, but you make sure that they're in equal total mass. And you melt them, and you also get their cooling curves. The cooling curves will give you their arrest points or the freezing points. And after getting all that, we put those things on a graph paper so that we can attain our phase diagram. And the graph paper, our graph will be temperature against composition. So this is what I summarized in this solution. That's why I'm telling you that the cooling curves for molten mixtures. These molten mixtures are going to be of various compositions, but equal total mass. Now this is very important. We use equal total mass so that we can get comparable results. So, but we only vary compositions. That's why I said cooling curves for molten mixtures of various compositions, but they must be of equal total mass, are first plotted. And these ones are going to give us our arrest points. And that's why we are saying, so the temperatures, so cooling curves for molten mixtures of various compositions but equal total mass are going to first be plotted. Like I said, if you look at your notes, we started by plotting those ones for pure components. And in pure components, I told them they are the ones with the trough of supercooling. Then we started plotting cooling curves for molten mixtures, where a liquid mixture first cools down, and then the one with the highest composition, the mixture, starts crystallizing out. And then you reach a constant temperature where all of the components are going to crystallize out. And then a decreasing temperature of our crystallized solid. So that's what we are meaning here. Cooling curves for molten mixtures of various compositions, but equal total mass are first plotted. These give the arrest points. Arrest points can also be called freezing points for these mixtures. So we are saying that the temperatures corresponding to the arrest points for a number of mixtures are plotted. So temperatures corresponding to the arrest points, after drawing your cooling curves, you get those temperatures on them. And we are saying that the temperatures corresponding to the arrest points for a number of mixtures are going to be plotted against the composition of the mixtures to obtain the phase diagram. So after getting the temperatures from the cooling curves, we plot what we call a phase diagram, and it's always temperature. The y-axis is going to contain temperature, and then the x-axis is going to contain composition, and we plot those points. After plotting those points, we always join these points with a line of best fit. And those points, on joining them, they must give you a V-shape. We draw a line of best fit through them, and this is what we call our phase diagram, and we are going to be looking at its structure in the next slide. Now this is a step-by-step how you can construct a phase diagram, and the good thing is that they are repeating what we have already been saying. So first step, you're going to have your pure, like if you want to draw a phase diagram for tin and lead mixture, you're going to get your pure tin and pure lead separately, and you melt them. After melting them, you are going to cool them purely, each of them separately, and you get the arrest point. That's why we are saying that each molten mixture is allowed to cool, but you are cooling while stirring, and the constant temperature at which each of them begins to freeze separately is going to be recorded. Now after that, we are going to start preparing mixtures, but the mixtures we are going to be preparing, we are going to be making sure that they are having various compositions, but all in all, they must have equal total mass. In each and every mixture, the total mass must be 50, if at all we have said to use 50 grams. But we are going to be varying the compositions of each component in the mixture, like using 25% tin and 75% lead, using 40% tin and 60% lead. But we must make sure that we use equal total mass in each and every experiment so that we can get comparable results. So that's why I'm saying the mixtures of various compositions of solid tin and lead are prepared, and then we are saying that each mixture is heated separately until it melts. Now the temperatures corresponding to freezing points are plotted. Temperatures corresponding to freezing points are plotted against composition to obtain a phase diagram. And our phase diagram is going to be in the following shape. So you must know this outline in your head. Pure components of substances are separately melted and then they are separately cooled, and you get their arrest of freezing points. After that, the mixtures of various compositions of the mixture are prepared. After preparing them, you also melt them, because remember that tin and lead exist in solid at room temperature, so they are going to be melted separately. After melting them, you obtain their cooling curves. You start cooling them while stirring them, and you get the arrest points, or the temperatures corresponding to their arrest or freezing points. After getting those temperatures, now you plot them on a phase diagram. And the phase diagram I've said is going to be temperature against composition. So pay attention to that. So let's look at that in the next slide. So this is an example of a phase diagram. Now a phase diagram, as I've already said, is always temperature. And it's temperature against composition. And composition, in this video, we decided to use percentages. But some videos use more fractions. But for this one, we are going to strictly remain on percentages. Now, the melting points here, the freezing points here, are going to be those ones of pure substances. Because look here, this one, now this axis is in terms of composition of tin. That means that here, remember this is a mixture. It means that here there is 0% tin. And that means that there is 100% of the other substance. If tin is 0%, that means that the other substance is 100%, which is lead. So this point here, the melting point of 327, or the freezing point, is for lead. I already told you, freezing point is the same as melting point. So 100% lead is here, and there's 0% lead, but there's 100% tin here. That means that this is the melting point for pure tin. Make sure that you label them to avoid forgetting them. So it's going to be pure freezing point or melting point of pure lead, and this is going to be freezing point or melting point of pure tin. Now what's going to happen is what we have been explaining. Now when you are going this side, you are going to see that you have started increasing the percentage of tin in the mixture, and when you consider tin as a non-volatile solid according to your colligative properties, the more increased tin, the more we cause depression in freezing point. So here, since lead is the one which is in the highest percentage, lead is going to crystallize out first, as we are calling. That's why we are saying that solid lead is going to crystallize out. But however, it's crystallizing out when we still have our liquid mixture, because it's just crystallizing out as we are cooling. Because the more we add tin, the more we depress its freezing point. And the more we cool, the more lead is crystallizing out. Reason being, lead is having the highest composition in the liquid mixture at this point. So that's why lead will be the one to crystallize out. Now lead is going to be crystallizing out until a point B is reached, whereby, now realize that the more lead is crystallizing out, the more our liquid mixture is going to contain more of tin. Like I told you, the one which is having a low composition does not crystallize out. So the more lead crystallizes out, the more the liquid mixture becomes richer in tin. So here in this triangle here, we label it as solid lead and liquid mixture. The solid substance is the one which is having the highest composition in that area, because as we cool, is the one that will be crystallizing out of the mixture. Now that will happen until a certain point is reached, like we stated in the notes. Here is labeled point B. Now point B is called the eutectic point. Now in the eutectic point can give us the eutectic temperature, which is a constant temperature at which both components in the liquid mixture solidify. and after solidifying they are going to give us solids. So the liquid mixture had liquid lead and molten lead and molten tin. After reaching this point here, they get converted to solids. Solid crystallizes out until point B is reached, and at this point it gets converted to a solid together with the other component in the mixture, and that point is called the eutectic point. That's why below that point, everything in the mixture gets converted to solid. So you're saying that this is the eutectic point where I've removed the points. Let me make the diagram a bit clear. Now the eutectic point corresponds to the eutectic temperature, and the eutectic temperature is a constant temperature at which both components of the liquid mixture are solidified, and in this case it's 183 degrees Celsius. Now that's the case for lead. Now what if we explain the graph coming from this side where tin is pure? So this is the pure freezing point of tin. Now here when we are going this side, we are going to be adding lead. Lead is going to be increasing. So when we add lead to the molten mixture of tin and we cool, its freezing point is going to be decreased. So the more we cool, the one with the highest composition. Now this area, tin is having the most composition. So tin is going to be crystallized out of the liquid mixture, but some of it is going to remain in the liquid mixture. That's why we say solid tin and liquid mixture. So as we cool, lead is crystallizing out, and as it crystallizes out, it makes the other component richer in the liquid mixture. Now the other component is going to be lead. Lead is going to be becoming richer in the liquid mixture. So it crystallizes out until a point is reached where both of the components in the mixture crystallize out, and this is still the same point, which is the eutectic point. So the eutectic point gives us two things. It gives us the eutectic temperature, and also it gives us the eutectic composition, which was 64% tin. And you get this by plotting. You'll be prompted to plot these graphs, and then these are lines of best fit through your points that you have plotted. The meeting point, you'll be labeling it as the eutectic point, and then the eutectic point will give you the eutectic temperature, and the eutectic temperature we also extrapolate to give us the eutectic composition. So this is it above the phase diagram. Above here always exists the liquid mixture. Now a question can tell you, describe what will happen when you cool a composition of 40% tin. Now what you do, that's why you label that composition. You label it using your ruler, but you don't do anything down here. You just use your arrows. Now you draw a dotted line, and that dotted line should come up to the slanting line. And after that, you draw a thick line flowing through this slanting line. Let me hope we are together until the eutectic point. After you reach the eutectic point, now you draw another line sloping, and this line should be dotted, and it should slope until the point they have reached the temperature they have told you. They might have told you to a temperature of 100 degrees Celsius, depending on the scale that you used on your graph. When they have told you to cool from, this could be 400. So that's how you plot. So you label them. You label the point at which you started cooling, and the point at which you reach the slanting slope, and then the point at which you reach the eutectic point, which is B, and then the point at which they want you to stop cooling. You may call it Z. Now let's look at some of the notes about this. So you're saying that a point B is the eutectic point. Let me hope you're seeing point B. Where point B is, let me highlight this. Point B is here. So you're saying that this point B is the eutectic point. I've already talked about the eutectic point. And you're saying that the eutectic mixture, you just extrapolate down. We are saying that to get its composition, you extrapolate a dotted line down to get 64% tin and 36% lead. And we are saying that the above diagram generally shows the addition of tin to molten lead results into lowering of freezing point of lead. Now this is what we have been covering in colligative properties. A video will be uploaded on this channel, so make sure that you check it out. So let's proceed to the next slide. Now we are going to explain this. Are you seeing this? From here, from point X, we cool this substance, or we cool that composition. This composition is not going to have any change in state and phase until it reaches this point Y on this slanting phase. Let me hope you are seeing here. When it reaches here, when it reaches the slanting slope, the component with the highest composition always starts to crystallize out first. And on crystallizing out first, when it reaches this thing, it crystallizes out first. And as the compound with the highest composition crystallizes out first, it makes the liquid mixture richer in the other component that is not crystallizing out first. And in this case, is going to be tin. The lead is going to be crystallizing out first because it's having the highest composition in the mixture. So the liquid mixture is going to be more richer in tin. And further, its freezing point is going to be decreased until point B, which is the eutectic point, is reached. And further, at this point, both components in the liquid mixture are going to solidify out. That's why we get solid lead and solid tin. Then from here, further cooling will lead to a decrease in the temperature or the cooling of the solid mixture. So that's how we explain when you are being prompted to describe what takes place when you cool a substance from a given temperature. First of all, you draw a dotted line from here. Let me change the highlighter. You draw a dotted line from here to the slanting curve, and then you label that line. And then from the slanting curve, you draw a line still dotted. I'm using a highlighter to the eutectic point, and then you draw a dotted line down to the point they have told you to stop on, and that's what you explain. You explain here, you explain here, you explain here, and you stop. And we can give you about 0.7½ max. So pay attention to it. So let's proceed. So we are saying that as the mixture cools, pure lead crystallizes out. The liquid mixture thus becomes richer in tin. Like I've been explaining, lead is crystallizing out because it's having the highest composition in the mixture. And then the one which crystallizes out leaves the mixture. That means that the liquid mixture will be more richer in the other components. That's why I say the liquid mixture thus becomes richer in tin as more lead crystallizes out. Hence freezing point of lead continues to be lowered. And then we are seeing that at a certain temperature, 2 degrees Celsius, both of these ones are going to crystallize out of the liquid mixture. And we are seeing that, and this temperature remains constant until the whole mixture solidifies. And this is the temperature that we call the eutectic temperature. Now let's look at some of the notes given. We are seeing that AB shows variation of freezing point of lead as tin is added. Now these are curves. And then BA shows variation of freezing point of lead as percentage of tin is being reduced. Now we can plot this diagram and it tells you to name the curves. Now I told you to name the curves according to what is taking place. So that means that AB is the freezing point curve of lead, and BC is the freezing point curve of tin. So you can either name it as AB or BA depending on the process. So in terms of BA, you look at where B is coming and A is going. It will be in terms of freezing point of lead as tin is being added, and the other one will be freezing point of lead as tin is being added, or lowering freezing point of lead. So we are saying curve BC. Curve BC shows variation in the freezing point. of tin as the percentage of lead in the mixture is reduced, or simply increasing melting point of tin as concentration of lead decreases. What about CB? CB shows variation of freezing point of tin as lead is being added, or refers to the lowering of freezing point of tin as the percentage of lead increases. So we are saying that the phases at point B are solid lead, solid liquid, solid tin, and liquid. Now remember that at point B, we say that that is the eutectic point. If you look at your notes that you have taken, point B is the eutectic point, and it's a point at which all the components in the mixture solidify out. So let's proceed to the next slide. So here we are presented a simple question, and in this question we are saying, describe the changes that will take place when a liquid mixture of the above system containing 40% tin is cooled from 400 degrees Celsius to 100 degrees Celsius. Now if you go back to that diagram, that's what I explained. I told you to plot a diagram and you label 400 degrees Celsius, we name it X, and then you draw a line to the slanting slope, and we name that point, we named it Y, and then from the slanting slope, you draw the line going with that slanting slope until the eutectic point, which was B, is reached, and then you draw a dotted line towards the temperature they have told you to stop on, which is 100, and you can put a point, let me say Z there. So you start explaining that line, that pathway one by one, and we are saying that from X to Y, this liquid mixture is going to cool without changing phase, like I've already explained earlier on. So the liquid mixture we are saying that the liquid mixture containing 40% tin is going to cool down without changing phase along XY. And we are saying that it's going to do so with a fixed composition. There is no going to be any change in phase and state up to point Y. Now remember that point Y is on the sloping region. If you go back to that graph you drew, let me hope you pause the video and you took the notes. If you go back to that graph you drew, point Y is on the slanting slope, and that's where on the slanting slope is where the component with the highest composition in the mixture solidifies out first. Now we are saying to a point Y, and we are saying that it's that point Y where solid leads begins to crystallize out. Now proceeding, we are saying that as lead solidifies out, because we have reached that slanting slope. Now this statement of as lead solidifies out, we are now explaining that slanting slope. As lead solidifies out, since it's the one with the highest composition in the mixture. So you're saying that as lead solidifies out with further cooling, the liquid mixture becomes richer in the other component that is not going to be crystallizing out. But here, instead of richer, we use the statement known as saturated. It's going to be saturated with the other component that is not crystallizing out, and that in this case is going to be tin. And we are saying that the freezing point of lead is further decreased along YB because the liquid mixture is becoming more saturated with tin. That means that the freezing point of lead that is being cooled is going to be further decreased along YB until point B is reached. Now remember we talked about point B, and that point B occurs at a given temperature, which is called the eutectic temperature. That's why we are saying that at B, the temperature, which is in our case on our graph was 183 degrees Celsius, you refer back to your graph, remains constant. And is the eutectic temperature, and that eutectic temperature at B is called an eutectic point, where both lead and tin solidify out at a constant temperature. So that's why we are saying At B, the temperature 183 degrees Celsius remains constant and both lead and tin solidify out together until all the liquid has solidified. So pay attention to that. So what point B? Point B is the eutectic point. The eutectic point refers to the point which at a constant temperature, all components in the mixture solidify out to form solids, and below that point we shall have solidified components of the liquid mixture. That's why we are saying that further cooling, now we are talking about this, further cooling below the eutectic point or the eutectic temperature results into no change of state or phase of the solid mixture. But in other words, it just causes further cooling of the solid mixture that we earlier formed. Now let's look at some of the simple Eutectic systems. Now the simple Eutectic systems, this is going to involve salt and water. For example, sodium nitrate and water system. So for this, we are saying that the phase diagram for such a system is obtained through the following steps. And we are saying that pure water is allowed to cool. So for sodium nitrate and water, this is not a common instance. However, we can bring it in most. So we are saying that we can prepare such simple eutectic systems by allowing pure water to cool. And we allow always to cool while stirring, and this must be at a constant temperature. The constant temperature at which pure water freezes is recorded, and usually that's 0 degrees Celsius. So we are saying that the solutions of various compositions of sodium nitrate, but these solutions must have equal volume so that we can obtain comparable results. What's going to vary is the composition of sodium nitrate and water. But in all experiments, we must use equal volumes of these solutions. So we are saying that each solution will then be allowed to cool, and it will be allowed to cool while stirring, and the constant temperature at which they freeze is going to be recorded. After that, we shall plot a graph of freezing point or temperature against composition to a given curve. Now notice that there is no this axis this side. Reason being, we cannot get melting point of pure solid sodium nitrate. Now remember, sodium nitrate is an ionic compound, and one of the characteristics you looked at for ionic compounds is that ionic compounds have high melting and high boiling points. So it's very difficult to get the melting point of solid sodium nitrate at the laboratory basis. So this is an example of a simple eutectic system, but it's rarely examined. However, this doesn't mean that you shouldn't understand it. So this is 0, reason being melting point or freezing point of water is 0 degrees Celsius. Point B is the eutectic point which gives us the eutectic temperature for the solution. Now the explanation of this graph remains the same, so I'm not going to waste time on this part because it's the same as the previous explanation. However, this one makes some sense, so we are going to be talking about this one. What happens when remember that there is high concentration of solid sodium nitrate, and when we are decreasing temperature, we are diluting, we're increasing water. So freezing point of sodium nitrate decreases with increase in water because water is now acting as the solid. And notice that the solubility of sodium nitrate, if you are to explain it this way, solubility of sodium nitrate is increasing with increasing temperature. So there are two explanations for that, because when you are going this way, temperature is increasing, and also solubility of sodium nitrate is also going to be increasing. That's why we are saying that if you look at the explanation given here, We are saying that the phase diagram of a system involving a salt and water is almost similar to that of the simple eutectic system involving two metals. That's why I've told you this explanation of this part remains the same, but I gave notes about it. So you pause the video and then you take the notes. And then we are saying that the only fundamental difference is that with the water to salt system, the melting point of salt in the phase diagram cannot be realized, and this is because the melting point of the salt is generally much higher than the critical temperature of water in the solution. But the general reason for this is because sodium nitrite is an ionic compound, and ionic compounds, we looked at them as compounds with one of the highest melting and boiling points. So on the laboratory basis, we can't attain them. Now for this slide, we have given a note, and we are saying that point A. Now if you look at your graph, we are saying that point A is 0 degrees Celsius, and this 0 degrees Celsius is always the freezing point of pure water. And we are saying line AB. Line AB shows variation of freezing point as temperature is as composition of the substance is being increased. So we are saying that line AB shows the lowering of the freezing point of water. Lowering of the freezing point of water as more sodium nitrite is added to it. Then what about point B? Point B, we have said that this is going to be our eutectic point, and we are saying that it's the lowest temperature which can be reached. The eutectic point, like I've explained, is that point where all the components in the liquid mixture solidify out. And we are saying that it is the lowest temperature which can be reached before the whole system solidifies. Now we are saying that it is also the only point at which ice, solid sodium nitrate, and the saturated solution of sodium nitrate are in equilibrium. Now we are saying that line BC shows solubility of sodium nitrate, and as I've explained, when you are going from B to C, when you are going up, it shows that the solubility of sodium nitrate in water increases with increasing temperature, which is the statement. That's why we are saying that solubility increases with increasing temperature. So pay attention to that. Now here are some of the explanations. Let me first clear this chart up. If you look at the explanations, we are having explanations of the above phase diagram, and we are saying that along AB, what happens along AB? If you look at AB, we are saying that the dilute solution of sodium nitrate is being cooled below 0 degrees Celsius. Now remember, at A, water has the highest composition, so that means that water is a solvent, and for any solid or another compound that we are adding, we shall be lowering freezing point of water. So that's what explains curve AB. So that's why we are saying along AB, a dilute solution of sodium nitrate is being cooled below 0 degrees Celsius. And we are saying that pure ice begins to crystallize out at a temperature less than 0 degrees Celsius. And we are saying this is because the added solute lowers the freezing point of water, and ice comes out first because the solution is more dilute. Now dilute, we are saying that is because this solution is containing more of the water other than any other component. Because water is present in excess, that means that it's going to be the one to crystallize out. The other sodium nitrite is acting as a non-volatile solid, which is decreasing or depressing the freezing point of water. So we are saying that as ice is formed, the solution becomes more concentrated. This is because water is crystallizing out, That's the ice which is being formed. And they say that the component that crystallizes out, the liquid mixture now becomes richer in the other component. That's why we are saying that the solution becomes more concentrated with sodium nitrate, because the other component is sodium nitrate. So we expect our liquid mixture or the solution now to be rich with sodium nitrate. And once it's more rich with sodium nitrate, that means that the freezing point of water is going to be further decreased. That's why we are saying that hence the freezing point is decreased further and more ice is deposited. Now we are saying that as the remaining solution gets more concentrated, eventually we reach an eutectic point, and that eutectic point is a point where both of them are going to crystallize out. That's why we are saying that as the remaining solution gets more concentrated, eventually both ice and sodium nitrate begin to crystallize out together, and this happens at a fixed temperature. That's why we are saying that negative 17.5 degrees Celsius is going to be our eutectic temperature. If you go back to that sketch, for people who drew it, you'll be able to observe it. Now we are saying that similarly, when the concentrated solution of sodium nitrate is cooled along CB, crystals of pure sodium nitrate will be deposited until negative 17.5 degrees Celsius. And we are saying that this is going to be the temperature when both ice and sodium nitrate crystallize out together. And the way we named this temperature, we named it as the eutectic temperature. And the point at which that occurs, we named that as our eutectic point. And the mixture at which that point is called the eutectic mixture. So let's proceed and see the other parts of the video. Now we have given a note, and in this note we are saying that when a solution of compound X is slowly cooled, it does so without changing phase along XB. If you look at the diagram, you'll be seeing these points. You go back to your first diagram, and we are saying that at point B, the solution solidifies at a constant temperature. Point B is the eutectic point. Until that means that if you ask you to define an eutectic point is going to be a point where the liquid mixture solidifies to form a heterogeneous solid mixture. But you are going to look at those definitions differently. So our eutectic point to the horizontal line, and you find that it will be negative 17.5 degrees Celsius. Now we are saying that until when all the solution are solidified into ice and sodium nitrate crystals. Now let's look at the examples of eutectics as we finalize this topic. Now we are saying that eutectics, now usually when we say these questions, we ask you at the end of the question, list 3 or 2 examples of other substances that show eutectic composition. And here you have them. There is cadmium and zinc, there is naphthalene and camphor, there is tin and bismuth, there is antimony and lead, and also benzene and naphthalene. So proceeding further, we look at the definitions of eutectic mixture. First of all, eutectic mixture can be defined in 2 ways. There is one from a solid to a liquid, or another one can determine from a liquid to a solid. One can determine from a solid to a liquid. Let me hope you get the difference. So you go with the one in which you find comfort, or which you can remember easily. But what we don't want you to miss out is this keyword. You need to include the word heterogeneous. So if you feel like you have spelling problems, make sure that you practice this word every day, because it's one of the marking points of the eutectic mixture. And we are saying that an eutectic mixture refers to the heterogeneous solid mixture which, when heated at a constant pressure. Now, what we want in this definition, we want to say constant pressure and we want to say constant temperature. So when you're taking your notes, make sure that you underline them so that you don't forget them. Heterogeneous solid mixture, and then you want to see a liquid, but this liquid which is being formed must be of the same composition as the solid mixture. That's why we are saying that an eutectic mixture is a heterogeneous solid mixture which, when heated at a constant pressure, will melt at a constant temperature, giving a liquid of the same composition as the liquid mixture. So take note of this. Now, alternatively, another person can also define it in another form, from the liquid to solid, and this is what we have been explaining in our graphs. So preferably you can opt for this one as your best definition if you have understood the previous explanations. And here we are saying an eutectic mixture refers to a liquid mixture in which at a constant pressure solidifies at a constant temperature. Now you can combine these two. Someone can say liquid mixture which at constant pressure and temperature is going to solidify to form a heterogeneous solid mixture. So hope you have seen heterogeneous does not miss in any eutectic mixture definition. So make sure that you include it. And also constant pressure and constant temperature, they must also be included because these conditions we need them specifically for this topic of physical chemistry. And then we are saying to form a heterogeneous solid, and also need to see this word of same composition, so make sure that you include it. So to wrap it up, eutectic mixture refers to the liquid mixture, and this liquid mixture which at a constant pressure solidifies at a constant temperature to form a heterogeneous solid mixture of the same composition as that of the liquid. Now, proceeding, we also have the definition of eutectic point, and we are saying that, as I've already been explaining, an eutectic point is going to be a point which two components of a liquid mixture solidify simultaneously. Now, this word is key. Or someone can say solidify all at once if you feel like this word will give you problems. But an eutectic point is a point at which two components of a liquid mixture are going to solidify simultaneously without changing composition at a fixed temperature. This is very important. We have been repeating this one in each and every definition. When you see a definition, something repeating, just know that that's one of the vital conditions required in the definitions. And if you lack it, you don't stand a chance of attaining any mark. So always pressure and temperature must be constant. So it's a point at which two components of the liquid mixture solidify simultaneously without change in composition at a fixed temperature and pressure. So proceeding, we also have the definition of the eutectic temperature, and we are saying that this is always the constant temperature which at constant pressure. So it's up to you to play around with these words. You find a way of including all these marking points. It does not matter your arrangement. So we are saying that an eutectic temperature is the constant temperature at which a liquid mixture is going to solidify at a constant pressure to form a heterogeneous solid. This word is key. A heterogeneous solid of the same composition as that of the liquid. So you should always make sure that you cram and understand those definitions. Make sure that conditions are always presented and don't leave any mark on the table. So let's look at the conditions for the formation of the eutectic mixtures. What are the conditions in which eutectic mixtures can be formed? So first of all, we are saying that pure crystals of the components should be separate from the mixture on cooling. And then two substances involved must be completely miscible when melted, because we don't want to get miscible liquids. On melting the two substances, you must make sure that they are miscible so that we get comparable results. And then eutectic mixtures can behave like compounds, but this is under the fixed conditions. So take note of this. This one is very common. Is very common in setting, and it's very hard to get a question under eutectics physical equilibria and you miss such a question. So here we are asking you, we are telling you that eutectic mixtures behave like compounds. And why is this the case? In the following ways. Now, number one, we say that they have sharp melting points, but this is at which condition? The condition here is at fixed pressure. So if you just say that they have sharp melting points, you are going to get it wrong. You must include the points to get the full mark. So they have sharp melting points at a fixed pressure. And then number three, they produce similar cooling curves like those of compounds. So both eutectics and compounds produce the similar cooling curves. And then number three, they have a fixed composition at a constant pressure. So this every condition is having at least a restriction apart from the second one. But these ones, they only have a fixed composition if at all pressure is constant or fixed. They only have sharp melting points if at all pressure is fixed. And then they produce similar cooling curves. So pay attention to that. So let's proceed. Now here we give reasons why eutectic temperature mixtures are not compounds. The previous ones were reasons why eutectic compounds can be considered as compounds. So number one reason, their compositions are going to vary with pressure. Now remember in the previous slide, we say that they are compounds because at a fixed pressure, their compositions are going to remain constant. And here we are saying that if you vary pressure, their compositions are going to vary. So their compositions vary with pressure. That's the meaning of the first point. And then they can be separated by physical means. Now remember that in your O-level, you are told that compounds cannot be separated by physical means. But for eutectic mixtures, they can be separated by physical means. So that prevents them from being considered as compounds. And then number three, which is so important, on microscopically examining eutectic mixtures, you will find that they exist as heterogeneous mixtures. So you find that many students are avoiding this statement, reason being of this word. But microscopic examination of eutectic mixtures shows that these mixtures are heterogeneous in nature, which is not the case with compounds. Compounds are not heterogeneous mixtures. And then number four, the composition of an eutectic mixture does not correspond to any known compound. Now you are told in some of the characteristics in your O-level that compounds have a fixed known composition, but for eutectics, their composition is not corresponding to any known compound on Earth. So let's look at some of the applications of eutectic mixtures. And we are saying that they can be used to form alloys. That's number one. Secondly, they can be used to form solders. Thirdly, they are used as safety appliances. They can be used in safety appliances like formation of plugs, and then they can be used in determining the identity of unknown organic compounds. And also, in industries, they can be used for lowering melting points of some substances. Now, whenever we are setting eutectic numbers, this is always the last question, because for every question we set, we always make sure we set a practical or an application of chemistry, especially in the field. This is one of the example questions that I gave. Now what you're going to be required, you are going to be required to plot this curve. You're going to plot it against percentage, and your x-axis is going to be percentage of naphthalene, your y-axis is going to be the melting point or freezing point. But you are given melting point, so your y-axis is going to be in terms of melting point, and you're going to be prompted to draw this phase diagram. I'm sure you are going to get a V-shaped curve, which will look like that. So you'll be required to join these points, and on joining them, you get your ruler, and then you join these 2 points using a ruler. You don't care, and then you also join these points using a ruler. And then the point of intersection, this is going to be your eutectic point. And then you do a horizontal line, this is going to be your eutectic temperature. And then this is going to be a liquid mixture. And then since the graph is again is percentage of naphthalene, then that means that this is going to be biphenyl plus solid biphenyl plus liquid mixture. And then this side is going to be solid naphthalene plus liquid mixture. And then here below the eutectic point is already solid mixture of these two substances. So solid biphenyl and solid naphthalene. So you label your graph properly. You also label their pure melting points because they are marked. So after doing that, then you pause the video and then you take the notes. You copy down the question, and then we see what's going to happen in the next slide. Now after plotting the graph, you are going to find that one of the eutectic temperature is 40 degrees, and the eutectic mixture is going to contain 48% naphthalene and 52% biphenyl. Now, part D is about what I explained, and I gave you the approach you are going to use. The perpendicular is drawn from 95 degrees to 50, and then you slope. And then from the graph, now these are some of the calculations. Now these calculations, we shall explain them in the next video about these exercises. We are going to make an exercise or a question that explains these calculations. But you can try to follow and write down this experiment so that you can be guided by your friends or teacher. Or you can try out the question on your own and see whether you come up with the following answers. The answers must be the same. So for the following slides, for the next slides, you are going to pause the video and then you take the notes. You take down the questions because they are going to be trial questions. And if you have a problem with physical equilibria still, I advise you to watch the video until you understand what's being examined. Then you engage in discussions with your friends so that chemistry gets used to you. So let's look at the next slide, which is having guiding questions. So you're advised to pause the video and then write down these questions. So you pause the video and write down the questions. And that's it for this video. This video has been presented to you by Mr. Walgembe Yusuf. And for those of you who have any questions about consultations, specifically chemistry and mathematics, you can reach me out on these numbers. Make sure that you are inboxing for serious issues. So we meet in the next video. You are advised to share the channel to your friends so that you can all benefit as a family. So see you in the next video, which will be the episode 2 explaining further physical equilibria. So stay tuned and subscribe to the channel for more updates.